Hello, everybody. Thank you for coming back from the break. My name is Andy Malice. As we said, I'm with Huawei and also the Services Area Director at the ONF. Let's see. And it works. Okay, so I'm going to give you an overview of some of the work that we're doing in the services area. And I'll be talking about the work going on in the different projects and working groups that we have, and introducing you to the architectural work that we're doing now. And also, I'm looking forward to a lot of the work that we'll be doing in 2016 in the group, so I'll be talking about that as well. So my name, as I said, is Andy Malice. I'm the Area Director for the ONF Services area, one of the 4 major areas in the ONF. We also have the specifications area, the marketing area, and the operator area. My deputy area directors are Fabian Schneider from NEC. Fabian is sitting in the back of the room, and so, there he is, he's moved over there, so he'll be keeping me honest in this talk. And we also have Shahar Staif from PCCW in Israel. The services area works on technical projects that enable applications and network operator services with SDN technologies. We also address issues related to the SDN architecture, framework interfaces, and methodologies. We have 5 major groups or projects going on in the group, in the area. There's architecture and framework, information modeling, layer 4 through 7 services, northbound interfaces, and security. And I'll be talking some more about each of these in turn. So first, I'd like to talk about architecture and framework. The chair is Dave Hood from Ericsson. Vice chair is Sybil Schlaler from NEC. Helps to standardize SDN by defining the broad set of problems that SDN architecture really needs to address. And also responsible for the SDN defining architecture, scope, and requirements. We've published 3 documents to date in this group. The architecture, issue 1, we're now working on issue 2, and I'll be talking about that. The architectural overview, and overall SDN scope and requirements. So in terms of the SDN architectural requirements and principles, there are a number of requirements and principles that really define SDN and the architecture for SDN. In terms of the requirements for the SDN architecture, we really need support for interoperability. That's the #1 requirement, and that's why we do work in standards, is to enable interoperability between different vendor implementations and different operator implementations and deployments. So we have support for interoperability based upon the open SDN controller interfaces, and everything, of course, that we do in the ONF is open. It's part of the name. Scalability and support for recursion to encompass all feasible SDN controller architectures. Now, we're talking about recursion later on in the talk. Applicability to a wide range of data plane resources. Policy and security boundaries are very important. Support for management interfaces, and I'll be talking about the management interfaces in my talk as well. And one thing that's also extremely important is coexistence with existing operator support systems and business support systems and other administrative or control technology domains. One thing we recognize is that operators can't afford to do a forklift upgrade on anything, so anything that's developed by the ONF really has to be compatible with operators already have deployed, or else it's not going to ever get into their network. So we have some architectural principles as well. The decoupling of control and data planes, that's one of the foundations of software-defined networking. Logically centralized control, that's one of the other foundations. And the exposure of abstract network resources and state to external applications, and that's something else I'll be talking about when I talk about the architecture in detail. So these are the basic SDN building blocks, and we've seen these a lot, so I can go through the slide very quickly. We basically have 3 layers or planes. There's the applications at the top, there's the controller in the middle, and there's the data plane at the bottom with the actual network elements such as switches and other hardware. And there are two very important interfaces in between these layers. Starting from the top, we have the northbound interface, which is also known as the application to controller plane interface. It's the interface between the applications at the very top and the SDN controller in the middle, which controls the network. Then you have the southbound interface, which is between the controller and the network elements. That's also known as the data plane to controller plane interface. So this right here is a look at the very high-level SDN architecture. On the very left, you have your operational support systems or overall management and orchestration. At the very bottom is the data plane. That's where you have your hardware and your switches and the actual network element resources. The box in the middle is the control plane. That's where you have your controller. The controller has a control logic, of course, coordination functions, and it has an agent which presents an interface going above. I just want to talk 1 second about the interface between the control plane and the data plane. That's the southbound interface. And there are a number of southbound interfaces that are defined in the industry. Two of them that we use in the ONF is OpenFlow, of course, and then there's the OpenFlow configuration protocol as well. So those are two of the possible southbound interfaces. There are others that are possible as well. And then looking above the controller to the applications, that's the northbound interface from the controller to the application plane. And you have any number of applications up there that want to use the resources of the network. And one thing that's important is that agent box in the controller presents a logical interface to the applications or an abstract interface to the applications for the network resources. So the applications don't need to know any of the specifics of the hardware or the actual boxes that we use down in the data plane. The controller presents an abstract representation of those resources to the application so that the applications can be written with an interface that they know and doesn't have to change depending on what hardware you actually use in the network. So if we take a look at this in more detail, that's the same box that was in the previous slide. I'm just going to look at some more detail in some of the boxes that we have on the left. So if you look at the SDN control logic, this kind of blows up what's going on in the SDN control logic. And the important thing there is you have a virtualizer. The virtualizer enables a number of things, such as the ability to have a number of different data planes, so we don't have to have even just one data plane in a network that's controlled by the same control plane. You can have a number of them, and they provide virtual resources and policies to the upper layers. And then you have the local network service box facing up that provides the northbound interface. Then if we take a look at the network element resources that are down the bottom, you see there's some additional detail in there. Again, you have virtualization going on in there. That allows us to tie in with NFV and actually have virtualized resources down at the bottom if you so wish. So you can have virtual storage, virtual computing, and so on, or actual storage and actual computing depending on whether you're using NFV in your network or not. And of course, there's forwarding going on in that plane as well. And finally, in the SDN applications, you actually have a number of things going on in an SDN application. You have a coordination function to coordinate with management. There's the actual application logic, and then there's the north side of the northbound interface talking to the controller in the middle. Then we have management, business boundaries, and recursion. And recursion is a very important concept in SDN as well. If we take a look at an SDN network, this is a network that we're calling the Blue network. It's called Blue, and it has let's call it the Blue service provider with a manager, a controller, and a physical data plane. So that's a network that's managed by and run by the Blue service provider. Well, they have a number of customers, or else you wouldn't be in business. So you need customers. We have a green customer, customer G, and a red customer, customer R. Well, if you take a look at what's going on in the green customer could actually be running their own virtualized network on top of the physical network. So what we're showing here is the customer G is actually a service provider, a virtual service provider with their own management, their own SDN controller, and their own data plane, but they're also taking advantage of the virtual data plane that's provided by the B service provider. So the B service provider is actually selling services to the green service provider, so that perhaps the green service provider doesn't have physical facilities in a particular part of the world, so they lease services from the blue service provider, or they don't have enough capacity in their own backbone, so again they lease services from the blue service provider. Now, if you take a look at customer R could be an application, or again, the customer R could be a service provider as well. And they're doing the exact same thing. They're running their own virtual service, and they could even use the green service provider to provide services by leasing capacity from the green service provider and leasing capacity from the blue service provider as well. So this is a very important example of how we can use recursion in SDN networks, where you have a number of different sets of SDN controllers, and they each use resources that's provided by the lower layer controller. So what's coming up next in architectural work? Well, in the upcoming year, 2016, we'll be working on what's known as Architectural Issue 2. We completed Architectural Issue 1, published in June of 2014. Well, there are a few issues with it that we'd like to improve upon for the next round or revision of the architecture. One was, it was about 68 pages, and some people complained that it's too long and it goes into too much detail. So what we'd like to do is streamline it going forward to make it easier to follow. And you can't find out everything about a topic by going to one place, because there's a lot of cross-linkages within the document. So we'd like to clean up its organization that way as well. The world has changed. NFV now is every bit as visible and important as SDN, so we want to make sure that we have a lot of inclusion for NFV as a basic part of the SDN architecture. So we'll be, in fact, we're doing a lot of work now with the ETSI NFV ISG group in terms of jointly issuing some documents that we've been working on the relationship between SDN and NFV, and we expect that work to continue, and we'll be including a lot of the results from that in the next issue of the SDN architecture. And we also have more insights that we've gained from issue 1. It's going to basically be extending it for NFV and making it more generally accessible to the non-technical public. So in terms of the technical changes that we're looking forward to, issue 1 was the architecture we've already spoken about. This right here may not be actually be what we have. This is just one of the proposals that we're discussing right now. And the major differences are, rather than looking at layers and recursion, we'll be spending a lot more time talking about the actual resources in the network and how multiple customers can be making use of the same resources simultaneously. So you see the blue, green, and red basically at the same layers rather than recursing on top of each other. So the new and improved topics that we'll be talking about are focusing on resources rather than planes, because we found that it's kind of difficult to show and talk about recursion in a static document. So we're trying to get away from that and talk about it more in terms of resources, controllers of resources, as well as managers and the network elements. We'll be talking a lot about virtualization of the network, and virtualization of the controllers. We'll be talking about what the differences are between an application and an SDN controller. And also we'll be adding explicit support for the intent northbound interface, and that takes me to the next portion of my talk. So here we have the northbound interfaces project, which is the next part I'd like to be talking about. The chair there is Dave Lenrow from HP. It's a large group, so we actually have 3 vice chairs. Pascal Menendez of Microsoft, Tina Tsao of Huawei, and Chris Chans from Sienna. This group develops the requirements, architecture, and working code, and working code is important, and I'll be talking about that, for northbound interfaces in order to lower the barriers for SDN application development, to make it much easier to write SDN applications. We create open source northbound interface and application interface code, APIs, for use, application programming interfaces for use with open source SDN controllers. And the 2 that we're focusing on initially are Open Daylight and ONOS. And we'll be working with other controllers as well, but those are the first 2 that we're concentrating on. And work will be focusing on the intent northbound interface. And you may ask, what's an intent northbound interface? Here we go. So here's the problem statement for the intent northbound interface. It's really nice if application developers could develop against a single northbound interface that can support many common use cases. So no matter what your use case is for SDN, and we heard a large number of use cases in Alex's talk previously, what we'd like to be able to do is be able to support all of those with one single northbound interface. So the challenge is to really find a set of abstractions that work for all these use cases, because as I said before, applications work against a set of abstractions in the network. They don't work against what the actual network does. They work against, or they program to an abstract representation of the network. So you want to be able to program against that abstract representation while hiding the details of the actual SDN network itself, its hardware, and so on. And it's really difficult to support multiple independently developed SDN applications without conflicts arising with being able to access the resources in the actual network. So the ONF architecture, which I talked about previously, actually talks about this and has an element in the block diagram called the virtualizer. I pointed out the virtualizer in one of the pictures earlier, that addresses this particular problem. So the process that receives the client-specific requests across the northbound interface then validates those requests against the policies and resources that are in the network that are accessible to this particular customer and application, and then translates the term into the underlying resources. That's the job of the virtualizer. So this is where the virtualizer is in the architecture. You remember this picture from earlier. So there's the virtualizer on the right that controls the resources, access to the resources and the policy in the data plane. So what intent-based networking does, it's an approach to managing a network that uses the common API for programming and abstractions to hide many of the network-specific details. And it's a portable way of integrating networked applications with the network infrastructure. So you don't have to worry about the specifics of protocols, vendors, device, chips. That's all taken care of in the abstraction and the virtualizer. And there's a single intent rendering engine, which is the single writer of flow rules and arbitrates all resource usage in the network. And I'll be talking about that in a minute. By extending the intent language and then implementing additional rendering modules to translate that intent into the southbound controller, and I'll be talking about that as well. So here's really a really nice overview of how you use intent in the network. Intent is basically what I want, not how to do it. So basically, you can say something like, I want my headache to stop. Right? You don't say, okay, I need to measure out the exact ingredients for an aspirin pill and then take this particular pill at a prescribed set of times. You know, I just want my headache to stop. So that's the intent. The prescription is how to actually make that happen. Another one is this user Bob is allowed to access the internet. That's the intent, not the prescription. The prescription is actually say, okay, the packets from Bob have to go through this particular path and then go out this particular port in the network in order to be able to access the internet. Or another example of intent is please cut my lawn, and then the actual prescription for that is take the mower out of the truck, fill it with gas and oil, pull the starter cord, and so on and so forth. So you see, that's the difference between intent and prescription. What I want is intent. How to do it with the commands, rules, and settings, and so on, is prescription. The important thing for intent is that it's independent of protocol, media, vendors. For prescription, that's where you start looking at the dependencies on the actual protocols, vendors, media, and so on. So the intent engine is the single source of what we call truth. You know, when you have an actual network with thousands or millions of devices and users interacting with thousands of elements of shared state, there can't be multiple uncoordinated control of the state of the network. There has to be one single point of control, especially control the resources, because you can't allocate the same resources to multiple users and multiple applications simultaneously. So in an SDN control, for example, an example of that would be multiple real estate agents simultaneously trying to sell the same house, right? You can't do that. You have to have one real estate agent who has management of that house in order to be able to sell it. So if an SDN controller is managing a fabric, which is an abstraction on top of a bunch of switches, it can't allow external applications also to have direct access of those resources. So the important thing of intent is that there is one function, which is the intent engine, which has the ability to manage all of the resources in the network. So our plans for intent for 2016 is we've already started an open source project called Project Boulder. This is open for anyone to work with. It's not just ONF members. You can, this work is coordinated at this particular URL, and these slides are public, so you don't have to write down the URL. All you have to do is download the slides from the conference, and you'll have access to the URL there. At that URL, you'll find all the documents, code, and email lists, and everything else, meeting calendars, wikis that allow you to participate in this open source project. It's going to produce an intent-based open source virtualizer implementation. It implements all the functionality that I talked about on the previous slides, and it's going to be used with both the Open Daylight and ONOS controllers to start, and then other controllers to follow that as well. And so that's basically our plans for 2016 for the northbound interface. Next, I'd like to talk about information modeling. This working group is chaired by Cam Land from Alcatel-Lucent and Nigel Davis from Sienna. This is responsible for the core information model that can be used as the basis for developing applications and forwarding technology-specific information models for other ONF projects in all the ONF areas and external SDOs as well. And I'll be talking about that. So they're currently working on technical enhancements to the ONF core information model and other associated models as well, working on tools to automate model generation and documentation. They do their modeling in a formal modeling language known as UML. And one of the things that they're working on very successfully is the automatic generation of Yang models and code from the UML. So that allows them to be able to basically specify the model for the network, and then from that model for the network, they can generate actual Yang code, which can be used in controllers and in network elements, and specific to those particular network elements and controllers. So what is information modeling? Well, we all do at least informal information modeling in our day-to-day work. And it's really simply the process of identifying, defining, and labeling and recording from viewpoint what you have as resources. So the key concepts and things in your problem space and the interrelationships between these key concepts, things, and resources. So when we analyze a problem, we develop and use terminology, and we develop structure. This is something that we all do in our day-to-day lives. And so they just do this, but in a formal way for networking and telecommunications. And when you do something like this, there's always a challenge of colliding terms and contradictory structure, or possibly so. So one of the things that they work very hard on is to provide the constraints and a degree of normalization so that everyone is talking about the same thing with the same terminology. And so the normalization removes unnecessary variety, emphasize the inherent complexity of the subject area, which is networking and telecommunications, and allows attention to be focused on the areas requiring exploration. And of course, this improves interoperability as well. So the key is the right degree of normalization in the work. And formal information modeling is a technique, which they use, that supports this purpose for things to be discussed in the solution space. So our vision in the ONF is one single industry-wide common open model for information networking. And this is something that we've been working very hard with, and not just by ourselves, but we've been collaborating with specifically with the ITUT and the TM Forum on this work as well, to make sure that we have a common information model that's not just used by the ONF, it's used by ITUT, it's used by TM Forum, it's going to be used by MEF, OIF, Broadband Forum, IETF, ETSI NFE, 3GPP, and so on as well. So this is basically work that we're leading, but is for the benefit of not just the ONF, but for the entire telecommunications industry as well. And the first result of all this collaborative work we've been doing is the release of the Core Model 1.0, which is published both in the ONF and consented in the ITUT as well as a recommendation G.7711. So this right here is just a representation of what the UML language for the model looks like. I'm not going to get that in any detail because I don't have the time to get into any detail as well. It's just the important top-level points are that it's partitioned into major units such as the core, forwarding technologies, intent, and specific views, and then divided into submodules for development independence, so you can have submodules that match current development needs as they change over time. So the benefits of the core model, they really help to reduce unnecessary variety in the industry. They allow all the equipment vendors to basically build to the same model in their equipment, which helps them get their equipment built faster and make sure that things will interoperate when it gets into a service provider network. And this is actually good for the service provider as well, because when they purchase equipment that they know has been built to the core information model, they know that there's a very good chance that things will interoperate in their network if they choose to build a multi-vendor network. So it's good for both vendors and service providers. It assists driving mappings between OpenFlow and service-level abstractions, which improves the coherence and enables the necessary bridges between OpenFlow and applications. It provides a formal basis for the work of the northbound interface and transport API teams to improve ONF internal coherence between all the work that's being done in the different groups in the ONF. And through the model, we assist in the rationalization across the industry of the representation of networks for the purpose of management and control. So the documents that we've published to date are the ONF Core Information Model version 1, base model 1.0, the Common Information Model overview, so it's an overview to help you get an understanding of how it all works, and guidelines that we used for when we wrote the model in the UML language, and we use a tool known as Papyrus, which helps to write the UML in the first place. So these are the guidelines for how we use Papyrus. It's an open source tool for writing UML. And note that the 1.0 model was constructed using Papyrus 0.10. It's an open source modeling tool. We've been working with the Papyrus group on improvements. We're now moving to what's known as Papyrus 1.1.1, which is documented for the next release, which will be mainly generated automatically using the model using a tool known as GenDocs, which can generate documentation from the model automatically based on the information in the model itself. So our plans for 2016 will be automatically generating Yang code, as I talked before, from the UML model. We'll have a controller model. So we're moving up from the network element models, and we're going to have a model of the controller itself, including all the components that you'd find in a typical controller. We're drawing from ONF architectural componentization activity and work that we've been working on jointly with the TM Forum. We're enabling support for function chaining and NFV virtual network functions. That's a very important part of the model going forward. Applying work as appropriate to the intent work that I talked about previously. We're enhancing our mappings to OpenFlow and the new versions of OpenFlow, going up to OpenFlow 1.5 and further. Enhancing support for SDN and optical and transport networks. We now have a new working group in the ONF called the Open Transport Working Group, and we'll be working very closely with those folks on making sure that all the work that they're doing is appropriately included in the modeling. And we also have a plugin for the Papyrus tool for external capabilities that take an appropriately formed model and a schema in a chosen language, Yang first, so we automatically can generate Yang, and then we'll be working with automatically generating JSON as well. So to summarize, the work in the services area leads the industry in the areas of SDN architecture, information modeling, and intent-based application support. We have plans on continuing expanding on this work in 2016 and beyond. We've also been working on SDN security and SDN layer 4 through 7 services, and unfortunately, due to time constraints, I didn't have time to include in this particular talk. I will be talking about that later on this afternoon in the ONF only part of the meeting at 3:30. And so the work in the services area leads to enhancing OpenFlow definition and extends the work in the ONF specifications area. And so we work very closely with those folks as well. So there's quite a bit to keep us busy in 2016. And with that, I'd like to thank you and ask if there's any questions. Yes. I think there's a microphone coming. Yeah.
Thank you very much. Ala Goldner from Alot Communications speaking. I wanted to ask actually about SDN-based layer 4.7 services, because
yes.
I know that you have a discussion group on layer 4.7 awareness, but actually, as far as I know, the documents were not introducing really an application awareness. So what are your plans in this regard? Yes,
they actually have a demonstration that's going to be going on here this week in concert with the ETSI NFV group. They're taking the work that they published and they've actually implementing it, and they're showing a demonstration of it this week at the show. So that's one thing to look for. That's being done in concert with the ETSI NFV ISG. And in terms of what's going to be going ahead in the future, there's a discussion on that's ongoing right now on the layer 4 through 7 email list in the ONF. So if you participate in that list, okay, there's right now they're actually opening basically opening for suggestions for work going forward. So if you have any, you can come talk to me, and you can also participate in the list as well, because that's exactly what we're working on right now, the agenda for next year.
Thank you.
There's another question right behind you.
Hi, Rick Talbot, Current Analysis. So speaking of information models, the way you've described it is you're trying to come up with one that all the different organizations would be able to use that for,
yes.
for SDN. I've heard some entities basically saying it's Yang and that's it. Would you care to address that as to why we're doing more than yang.
Absolutely. Well, we are certainly doing yang. If you noticed, I mentioned that we're automatically generating yang from the UML-based model. So certainly yang is an important part of the work. But yang really is it's a lot like SNMP. Okay, but basically you can look at yang as the next version of SNMP, in that if you just write yang against your device specification, what you end up with is device-specific yang model, right? It's not really general at all. It's not something that you can use for anything other than that one use. So what we're trying to do here is we're trying to generalize. We're trying to say, okay, this is one specific core model which encompasses anyone's hardware, anyone's software, all the specific protocols of interest, and then we generate the yang code from that. That allows you to generate yang code, which is then usable by a large number of vendors that they can just plug in to their their management systems, and it's usable by a large number of service providers that they can plug into their OSSs as well. You don't have to worry about each vendor generating yang code that's specific to their particular equipment, for example. Anyone else? Yes.
Donation from EJL Wireless Research. All the effort you have done as like open network, open infrastructure foundation is try to do improve interoperability, make all the ecosystem more effective, efficient, right? Mm-hmm. And look at so many organizations. And we, as communication, the interoperability is really depend on the protocols.
Absolutely.
And you exchange information exactly, clearly, and communicate it between different modules. And how do you make sure this could happen? Because if you just have ecosystem, have the good intent, have the descriptions, but you have to be accurate to the bit or byte. But how do you resolve this problem with this kind of architecture?
Well, I don't see it as a problem. It's basically doing exactly what you said, which is being accurate with what you write, and also basically having very clear communications with the other STOs to make sure that, that there's a clear understanding of which STOs are working on what parts of the overall problem set that you see networking is. One thing that helps is that we have people who are active in the various other bodies as well. For example, I personally am active not only in the ONF, but I'm very active in the IETF. I've been in the past very active in the Broadband Forum and ITUT, and so it helps to have people who are active in more than one place so they can help work as liaisons. But we also have very active formal liaison relationships with the other bodies, so they're clear with what we're working on and we're clear with what they're working on, and we make sure that everyone has a good understanding of that. And Mark's putting up his hand because
after lunch, there is a talk that Kurt Beckman is going to provide that addresses the initiatives underway in the ONF to foster interoperability. So make sure you attend that talk, because he's going to talk about the specifics of how we're actually ensuring overflow.
And the timer over there tells me that we're out of time. So I'd like to thank you all very much, and I'm looking forward to the panel session that comes up next. Thank you.